Welcome, cosmic travelers, to another journey into the profound mysteries of existence. Tonight, we embark on an epic exploration of cosmology, the very study of the universe itself. From the whispers of ancient thinkers gazing at the stars, to the grand pronouncements of modern physics, we will trace humanity's relentless quest to understand our cosmic home. Settle in, let the sounds of the universe wash over you, and prepare to have your mind expanded. Before we dive deep, if you find solace or inspiration in these cosmic tales, consider giving this video a like, share your thoughts in the comments below, and perhaps share it with someone else who might also find comfort in these grand narratives. Your engagement helps these stories reach more curious minds. Now, let's begin our voyage into the boundless cosmos. The universe, a concept so vast it often escapes the grasp of our everyday experience, has captivated humanity since the dawn of conscious thought. From ancient campfire stories sketching out the firmament to the most advanced observatories peering into the fabric of space-time, our innate curiosity about existence itself has fueled an endless quest for understanding. This quest, this profound intellectual journey, is what we call cosmology. The word cosmology itself is a beautiful fusion, born from the ancient Greek cosmos, meaning the universe, the world, and logia, the study of. It's an inquiry into the very nature of everything, a discipline that bridges the most profound philosophical questions with the rigorous demands of scientific observation. The term, as we understand in English today, found its footing in the mid-17th century, a time of burgeoning intellectual exploration. By the 18th century, German philosopher Christian Wolff solidified its place, defining it as a branch of metaphysics dedicated to the general nature of the physical world. But cosmology is not a monolithic concept. It branches out into myriad forms, reflecting the diverse ways we humans attempt to make sense of our surroundings. There is religious and mythological cosmology, a rich tapestry of beliefs woven from ancient creation myths and eschatological traditions. These are the stories told around fires, whispered in temples, passed down through generations, attempting to explain not just how the world came to be, but why. Then, within the realm of scientific astronomy, cosmology narrows its focus, primarily concerning itself with the chronology of the universe, its timeline, its evolution, its grand narrative as revealed by data. Our journey tonight, however, will delve primarily into the realm of physical cosmology. This is the scientific bedrock, the rigorous study of the observable universe's origin, its immense structures, its dynamic behavior, and ultimately, its ultimate fate. It's where the laws of science intersect with the deepest cosmic mysteries. Here, astronomers and physicists work hand in hand with philosophers, metaphysicians, philosophers of physics, and those who ponder the very nature of space and time. This shared territory means that physical cosmology can, at times, venture into propositions that are not always strictly testable, relying on foundational assumptions that form the very lens through which we view the cosmos. It's a sub-branch of astronomy, yet its scope encompasses the universe as a whole, a magnificent endeavor to paint a complete picture of reality. At the heart of modern physical cosmology lies the Big Bang theory. This isn't just a theory, it's our prevailing framework, a grand tapestry that weaves together observational astronomy with the intricate world of particle physics. More specifically, our current understanding is best described by the lambda-CDM model, a standard parameterization of the Big Bang that incorporates the enigmatic forces of dark matter and dark energy, which we will explore in a later segment. Theoretical astrophysicist David N. Spergel beautifully characterizes cosmology as a historical science. Think about that for a moment. He states that when we look out in space, we look back in time. This profound statement encapsulates the very essence of astronomical observation. Due to the finite, albeit astonishingly fast, speed of light, Every photon that reaches our telescopes from distant galaxies carries with it the story of the past. The light from a galaxy millions of light years away began its journey millions of years ago. We are, in effect, cosmic archaeologists, sifting through ancient light to reconstruct the universe's autobiography. The journey of understanding our place in the universe has been a long and winding one, punctuated by profound shifts in perspective, true epistemological ruptures that reshaped our very understanding of reality. For centuries, our worldview was geocentric. The Earth, our home, was believed to be the unmoving center of the universe, with the sun, moon, planets, and stars all revolving around us in perfect celestial spheres. This Ptolemaic system, meticulously crafted by the Greek astronomer Ptolemy, reigned supreme for over a millennium. It was a comforting, human-centric vision, yet ultimately flawed. Then came the intellectual earthquake of the 16th century. Nicholas Copernicus, a Polish astronomer, dared to challenge this established order, proposing a heliocentric system where the sun, not the Earth, lay at the center of our solar system. This wasn't just a mathematical adjustment. It was a radical shift in perspective, a humbling realization that our home world was but one planet among others, orbiting a star. Johannes Kepler and Galileo Galilei, building upon Copernicus's work, further solidified this new understanding, providing observational evidence that shattered the old paradigms. Galileo's telescopic observations of Jupiter's moons, clearly orbiting Jupiter and not Earth, were a definitive blow to the geocentric model. This period marks one of the most famous examples of an epistemological rupture in physical cosmology, a fundamental overturning of how we knew what we knew. The stage was set for another titan of science, Isaac Newton. In 1687, he published his monumental work, Principia Mathematica, a text that laid the foundation for modern physics. Within its pages, Newton unveiled the law of universal gravitation, a force that permeated all matter, governing the fall of an apple and the orbit of planets with equal precision. This provided the long-sought physical mechanism for Kepler's laws of planetary motion and, crucially, allowed for the resolution of anomalies in previous systems caused by the subtle gravitational tugs between planets. Newton's cosmology represented a crucial philosophical advance. It established the Copernican principle on a grander scale. The physical laws governing an apple falling to Earth were the same laws that held the moon in its orbit and guided the planets around the sun. There was no special celestial physics, no divine ethereal substance in the heavens that defied earthly rules. The universe was governed by a singular, elegant set of laws, applicable everywhere to everything. This was a profoundly unifying concept, a beacon guiding future scientific inquiry. Modern scientific cosmology, as we largely understand it today, is widely considered to have truly begun in 1917 with Albert Einstein's publication of his final modification of general relativity. In his paper, Cosmological Considerations of the General Theory of Relativity, Einstein presented a revolutionary framework for understanding gravity as a curvature of space-time. This new theory prompted a flurry of intellectual activity among cosmogonists like Willem de Sitter, Carl Schwarzschild, and Arthur Eddington, who began exploring its astronomical ramifications. General relativity enhanced the ability of astronomers to study incredibly distant objects, allowing them to probe the universe with unprecedented depth. Crucially, physicists began to question a long-held assumption that the universe was static and unchanging. This assumption of a static universe had deep roots, stemming from philosophical comfort more than scientific necessity. But the universe, as it turned out, was anything but static. In 1922, a brilliant Russian cosmologist named Alexander Friedmann introduced the radical idea of an expanding universe that contained moving matter. His mathematical solutions to Einstein's equations showed that a dynamic, evolving cosmos was not only possible, but perhaps even necessary. Parallel to this theoretical revolution, a long-standing debate about the fundamental structure of the cosmos was reaching its crescendo, the Great Debate. From 1917 to 1922, early cosmologists grappled with a monumental question. Were the faint, spiral-shaped nebulae seen through telescopes merely clouds of gas within our own Milky Way, or were they entirely separate galaxies, vast island universes far beyond our own? Astronomers like Heber Curtis argued forcefully for the island universe hypothesis, believing these nebulae to be distant galaxies comparable to our own. On the other side, Harlow Shapley, a prominent astronomer at Mount Wilson Observatory, championed the model of a cosmos made up solely of the Milky Way, a vast but solitary stellar empire. This profound difference of ideas culminated in the famous Great Debate on April 26, 1920, at the meeting of the U.S. National Academy of Sciences in Washington, D.C. It was a clash of titans, a scientific showdown that would redefine our understanding of the universe's scale. The debate, however, wasn't truly settled by rhetoric. It required definitive observational evidence. And that evidence came from the keen eyes and persistent dedication of Edwin Hubble. In 1923 and 1924, while observing the Andromeda Nebula, Hubble detected Cepheid variable stars within it. These particular stars have a crucial property. Their pulsation period is directly related to their absolute luminosity. By measuring their apparent brightness, Hubble could accurately calculate their distance. What he found was staggering. The Andromeda Nebula was not within the Milky Way, but millions of light-years beyond it. It was, unequivocally, a separate galaxy, a true island universe. Hubble's discovery was a turning point. It shattered the notion of solitary Milky Way and ushered in a new understanding of a cosmos teeming with countless galaxies, each a sprawling collection of stars, gas, and dust. This expanded universe, far grander than anyone had previously imagined, profoundly influenced subsequent cosmological models. Building upon Friedmann's work and Einstein's general relativity, the possibility of an expanding universe gained traction. Einstein himself had introduced a cosmological constant into his equations to maintain a static universe, a movie later called his biggest blunder. But it turned out this constant, depending on its value, could indeed lead to an expanding universe. It was the Belgian priest and physicist Georges Lemaitre who, in 1927, formally proposed the Big Bang model. He theorized that the universe began from an incredibly hot, dense state and has been expanding ever since. This audacious idea, initially met with skepticism, received crucial corroboration from Edwin Hubble in 1929. Hubble, observing galaxies, discovered the redshift phenomenon. Light from distant galaxies was systematically shifted towards the red end of the spectrum, indicating that they were moving away from us. Furthermore, the farther away a galaxy was, the faster it appeared to be receding. This elegant relationship, now known as Hubble's law, provided compelling observational evidence for a uniformly expanding universe. The final, undeniable piece of the Big Bang puzzle arrived in 1964 with the serendipitous discovery of the cosmic microwave background radiation by Arno Penzias and Robert Woodrow Wilson. This faint, uniform glow of microwave energy detected from all directions in space was precisely what the Big Bang model predicted. The residual heat, the afterglow, of the universe's scorching hot infancy. These monumental findings, Hubble's redshift and the CMB, were the first decisive steps in ruling out many alternative cosmological theories, solidifying the Big Bang as our dominant paradigm. Since around 1990, we've entered what many now call the golden age of cosmology. This era has been marked by several dramatic advances in observational cosmology, transforming it from a largely speculative science into a predictive one with astonishing agreement between theory and observation. Satellites like COBE, WMAP, and Planck have provided incredibly detailed maps of the cosmic microwave background, revealing subtle temperature fluctuations that are the seeds of today's large-scale cosmic structures. Massive galaxy redshift surveys, such as 2DFGRS and SD-SES, have mapped the distribution of millions of galaxies, unveiling the intricate web of cosmic filaments and voids. Observations of distant supernovae and gravitational lensing have provided further crucial data points, allowing us to precisely measure the expansion history of the universe. These observations have consistently matched the predictions of the cosmic inflation theory, a refined version of the Big Bang model that proposes an incredibly rapid, exponential expansion in the universe's earliest moments. And within this framework, the Lambda-CDM model has emerged as our standard cosmological model. It's a remarkably successful description of the universe, incorporating ordinary matter, and dark energy to explain the cosmic structures we observe and the universe's expansion history. Of course, the scientific journey is never without its detours and corrections. In 2014, the BICEP2 collaboration announced what seemed like a groundbreaking discovery: the detection of the imprint of gravitational waves in the cosmic microwave background, providing direct evidence for cosmic inflation. However, later analysis revealed that this signal was unfortunately spurious, primarily due to interstellar dust within our own galaxy. Such setbacks, though initially disappointing, are a vital part of the scientific process, reminding us of the rigorous scrutiny and self-correction inherent in the pursuit of truth. Our current understanding, as refined by these decades of dedicated research, paints a truly awe-inspiring picture. As of December 2014, detailed analysis from the Planck mission revealed that our universe is approximately 13.8 billion years old, and its composition is stranger than fiction. Only 4.9% atomic matter, the stuff of stars, planets, and ourselves, with the vast majority being the mysterious dark matter at 26.6% and the even more enigmatic dark energy at a staggering 68.5%. These dark components, though invisible, exert immense gravitational and expansive influences, shaping the universe on its grandest scales. While physical cosmology focuses on the measurable, the observable, and the testable, it's crucial to remember that humanity's search for understanding extends beyond the scientific. Religious or mythological cosmology offers a different kind of truth, a narrative built on beliefs, ancient literature, and traditions. These creation myths, found in almost every culture and religion, serve to answer fundamental questions of origin and purpose, often through powerful metaphors and symbolic narratives. Scholar Mircea Eliade and his colleague Charles long categorized these creation myths into 5 broad types, based on recurring motifs. We find myths of creation ex nihilo, where the universe springs from the thought, word, dream, or even bodily secretions of a divine being. There are earth diver creation myths, where a divine being dispatches a diver, often a bird or amphibian, into a primordial ocean to bring up mud or sand, which then expands to form the terrestrial world. Emergence myths describe progenitors journeying through a series of underworlds or metamorphoses before finally arriving in the present world. Some cultures conceive of creation by the dismemberment of a primordial being, where the body parts of a sacrificed deity form the various elements of the cosmos. And finally, there are myths of creation by the splitting or ordering of a primordial unity, like the cracking of a cosmic egg or the imposition of order upon a chaotic void. These diverse narratives, though not scientific, speak to a deep human need to contextualize our existence within a larger story. Cosmology, in its broadest sense, fundamentally grapples with the world as the totality of space, time, and all phenomena within it. And historically, its scope was vast, often intertwined with religion and philosophy. Even today, some questions about the universe lie beyond the reach of scientific inquiry, though they remain profoundly important. These are the questions that philosophy grapples with, using different modes of reasoning like dialectics. Consider some of these profound, extra-scientific inquiries. What is the origin of the universe? Does it have a first cause, if any at all? Is its existence necessary? Or could it simply not be? These questions touch upon concepts like monism, pantheism, emanationism, and creationism, each offering a unique philosophical stance on ultimate origins. What are the ultimate material components of the universe? This delves into debates between mechanism, dynamism, holomorphism, and atomism, different views on the fundamental building blocks of reality. Perhaps most poignantly, what is the ultimate reason, if any, for the existence of the universe? Does the cosmos have a purpose, a teleological goal towards which it strives? And finally, does the existence of consciousness play a role in the existence of reality itself? How do we even know what we know about the totality of the cosmos? And can cosmological reasoning reveal deeper metaphysical truths? These are the enduring questions that invite us to contemplate beyond the measurable, to ponder the very fabric of meaning in the universe. The roots of ancient Greek cosmology, a vital intellectual tradition, are often attributed to Anaximander, a pre-Socratic philosopher who, in the 6th century BCE, posited a universe of infinite, boundless primordial matter from which all things emerged. His insights, however rudimentary by modern standards, marked a profound shift towards a more rational and systematic attempt to understand the cosmos, laying some of the earliest groundwork for the grand intellectual edifice we now call cosmology. From these first whispers of cosmic inquiry, through the profound ruptures of scientific discovery, to our current age of unprecedented understanding, the story of cosmology is the story of humanity's ceaseless wonder and relentless pursuit of the truth, a truth that continues to unfold, one luminous revelation at a time. From the tranquil shores of earth-centered thought, we've journeyed across vast intellectual oceans, propelled by curiosity and the relentless march of discovery. We've seen how our understanding of the universe transformed from a static, comfortable celestial sphere to a dynamic, expanding cosmos, a paradigm shift that laid the groundwork for the monumental insights that would follow. Now, we delve deeper into the very fabric of existence, exploring the grand narrative that defines our modern cosmological understanding, the Big Bang. Imagine, if you will, a moment not just of creation, but of an unfolding, not an explosion in space, but an explosion of space itself. This is the essence of the Big Bang theory, the cornerstone of modern physical cosmology. It paints a picture of a universe that began incredibly hot and dense, a primordial cosmic soup, and has been expanding and cooling ever since. This isn't just a philosophical musing. It's a scientific framework, meticulously constructed and refined over decades, woven from observational astronomy and the intricate principles of particle physics. Our journey through this cosmic origin story begins with a profound simplicity. The universe is not eternal and unchanging, but has a finite age. Theoretical astrophysicists, peering through the lens of light's finite speed, describe cosmology as a historical science. When we gaze at distant galaxies, we are not just seeing light from faraway places, but light that has traveled for billions of years, offering us a glimpse into the universe's ancient past. We are quite literally looking back in time. The conceptual seeds of the Big Bang were sown by revolutionary thinkers. In 1917, Albert Einstein, with his groundbreaking theory of general relativity, inadvertently provided the mathematical scaffolding. While Einstein initially introduced a cosmological constant to ensure a static universe, a concept he later called his biggest blunder, his equations, when left unconstrained, suggested a dynamic, evolving cosmos. This idea of a non-static universe was soon explored by cosmogonists like Willem de Sitter, Carl Schwarzschild, and Arthur Eddington, who began to unravel the astronomical implications of general relativity. Then, in 1922, Alexander Friedman introduced the radical notion of an expanding universe, one filled with moving matter. This was a profound departure from the prevailing static models. But theoretical frameworks often need observational anchors to truly take hold. And the universe, in its own enigmatic way, was preparing to reveal those anchors. Around the same time, a pivotal intellectual clash, famously known as the Great Debate, was unfolding. This was a disagreement among astronomers about the very architecture of the cosmos. Were the fuzzy, spiral nebulae seen through telescopes merely gas clouds within our own Milky Way galaxy? Or were they independent island universes, galaxies in their own right, incredibly distant from our celestial home? Heber Curtis championed the idea of these nebulae as separate galaxies, while Harlow Shapley advocated for a cosmos comprised solely of the Milky Way. The resolution to this grand cosmic dispute came in 1923 and 1924, thanks to the meticulous observations of Edwin Hubble at the Mount Wilson Observatory. Hubble, a towering figure in astronomical discovery, identified a specific type of pulsating star, known as Cepheid variables, within the Andromeda Nebula. These stars have a predictable relationship between their pulsation period and their intrinsic luminosity, making them cosmic standard candles. By measuring their apparent brightness, Hubble could determine their immense distances. His calculations unequivocally placed the Andromeda Nebula far beyond the boundaries of the Milky Way, settling the great debate and revealing a universe teeming with countless galaxies. This revelation was monumental, but the most profound piece of the puzzle was still to come. The idea of a universe that began from a singular, hot, dense state was first formally proposed by the Belgian priest and physicist Georges Lemaitre in 1927. His model was a direct implication of an expanding universe, where tracing the expansion backward in time would lead to a point of ultimate compression. Just 2 years later, in 1929, Edwin Hubble delivered another staggering blow to the static universe model. He observed that the light from distant galaxies was consistently redshifted, meaning their light waves were stretched towards the red end of the spectrum. This redshift was directly proportional to their distance. The farther away a galaxy was, the faster it appeared to be receding from us. This phenomenon, known as Hubble's law, was the direct observational evidence for an expanding universe, providing powerful corroboration for Lemaitre's theoretical Big Bang model. However, the universe had one more incredible secret to unveil. For decades, theorists had predicted a faint afterglow from the Big Bang, a residual radiation permeating all of space, a kind of fossil light from the universe's infancy. In 1964, Arno Penzias and Robert Woodrow Wilson, working with a large horn antenna at Bell Labs, stumbled upon this cosmic background radiation. It was a persistent, uniform noise coming from every direction that they couldn't explain away. This discovery of the cosmic microwave background radiation, or CMB, was the definitive smoking gun for the Big Bang, earning Penzias and Wilson the Nobel Prize and transforming cosmology from a largely speculative field into a precise science. The CMB provided a snapshot of the universe when it was only about 380,000 years old, a time when it had cooled enough for atoms to form and light to travel freely. These foundational discoveries, Hubble's expanding universe and the cosmic microwave background, firmly established the Big Bang as the leading model for the universe's origin and evolution. But as our observational capabilities advanced, new mysteries emerged, revealing that the universe held far more secrets than we could have ever imagined. Since the 1990s, we've entered what many call the golden age of cosmology. Satellite missions like COBE, WMAP, and Planck have meticulously mapped the cosmic microwave background, revealing tiny temperature fluctuations that are the imprints of the early universe's quantum seeds. These minute variations are the origin points of all the large-scale structures we see today: galaxies, clusters, and superclusters. Simultaneously, large galaxy redshift surveys, like the two DFGRS and SD-SES, have created stunning three-dimensional maps of a universe, tracing the distribution of matter across billions of light-years. Observations of distant supernovae and gravitational lensing effects have further refined our understanding of cosmic expansion. These incredible advances didn't just confirm the Big Bang. They led to a significant modification and refinement of the theory, the concept of cosmic inflation. Inflation proposes that immediately after the Big Bang, the universe underwent an incredibly brief but extraordinarily rapid period of exponential expansion, stretching space by an unimaginable factor. This inflationary epoch elegantly solves several outstanding puzzles of the standard Big Bang model, such as why the universe appears so flat and why the CMB is so remarkably uniform across the sky. The combination of the Big Bang with cosmic inflation, along with two other enigmatic components, dark matter and dark energy, forms the bedrock of our current standard model of cosmology, the Lambda-CDM model. Let's turn our attention to these unseen forces that dominate our universe, starting with dark matter. For decades, astronomers observed a curious discrepancy. Galaxies were rotating too fast for the amount of visible matter they contained. The gravitational pull from stars, gas, and dust simply wasn't enough to hold them together. They should have flown apart. This led to the inescapable conclusion that there must be an invisible, gravitationally influential substance at play. We call it dark matter. Dark matter doesn't interact with light or other forms of electromagnetic radiation, which is why it's dark. We can't see it, touch it, or directly detect it with current technology. Yet, its gravitational fingerprints are everywhere. It shapes the way galaxies form and cluster. It bends light from distant objects through a phenomenon called gravitational lensing, and it influences the cosmic microwave background. Current estimates suggest that dark matter makes up about 26.6% of the universe's total mass energy content. It's a fundamental component, literally the scaffolding upon which the visible universe is built, yet its true nature remains one of the greatest mysteries in modern physics. Scientists are actively pursuing various candidates for dark matter, from exotic subatomic particles to primordial black holes, but the definitive answer eludes us. Then, there is dark energy, an even more perplexing enigma. In the late 1990s, observations of distant supernovae, acting once again as cosmic standard candles, revealed something truly astounding. The expansion of the universe is not slowing down as expected due to gravity, but is actually accelerating. This was a profound shock, as gravity should be pulling everything together. To explain this accelerated expansion, cosmologists propose the existence of a repulsive force, a kind of anti-gravity that permeates all of space. This force is what we call dark energy. Dark energy is thought to be an intrinsic property of space itself, a constant energy density that doesn't dilute as the universe expands. It acts to push galaxies apart, driving the accelerated expansion, and its dominance is staggering. Current measurements indicate that dark energy constitutes an astonishing 68.5% of the universe's total mass energy budget. It is the dominant component of our universe, yet its nature is even more mysterious than that of dark matter. It could be a cosmological constant, a property inherent to space-time, or it could be a manifestation of a dynamic field, changing over time. Understanding dark energy is perhaps the most pressing challenge in cosmology today, as it dictates the ultimate fate of our universe. Will the expansion continue indefinitely, leading to a big rip where even atoms are torn apart, or will a subtle shift in dark energy's behavior lead to a different destiny? These are questions that echo through the void, awaiting answers. So, when we summarize our cosmic inventory, we find a truly peculiar composition. The visible matter that makes up stars, planets, and ourselves accounts for only a paltry 4.9% of the universe. The vast majority, over 95%, is comprised of these two invisible, enigmatic entities, dark matter and dark energy. This realization is both humbling and exhilarating. It reveals the immense scope of our ignorance, yet also the vast frontiers of discovery that lie ahead. The Big Bang, cosmic inflation, dark matter, and dark energy. These are not just abstract concepts. They are the cornerstones of our most comprehensive understanding of the universe, built upon meticulous observations, rigorous theoretical frameworks, and a collective human desire to comprehend our place in the grand cosmic tapestry. This incredible narrative of creation and evolution, of unseen forces sculpting galaxies and driving the very expansion of space, continues to be refined with every new discovery, inviting us to look deeper think bigger, and ponder the ultimate questions that transcend the boundaries of our observable universe. What lies beyond this cosmic horizon? What other mysteries await the persistent gaze of science? These are the questions that fuel our quest, guiding us into the unknown and reminding us that the universe is an endless source of wonder, a story that is always, always still unfolding. Having journeyed through the astounding revelations of scientific cosmology, from the Earth-centered visions of antiquity to the expanding, dark energy-dominated universe of today, we now arrive at a fascinating crossroads. Here, the meticulously measured and rigorously tested framework of physics and astronomy gracefully steps aside, allowing for a broader, deeper contemplation of existence itself. This is where we delve into the realms beyond science, where the universe, in all its profound mystery, has been explored through the ancient echoes of myth, the intricate tapestries of philosophy, and the most enduring questions of the human spirit. The very word cosmology, as we've explored, carries within it this dual heritage. While in modern science, it signifies the study of the universe's physical chronology, its origin, evolution, and ultimate fate, its origins are far more expansive. Coined in English in 1656 as a speaking of the world, and later formalized in Latin by the German philosopher Christian Wolff to denote a branch of metaphysics, cosmology has always been inherently entwined with understanding the nature of the universe, not just its mechanics. This deep historical root reminds us that the quest to comprehend the cosmos is not solely the domain of equations and telescopes. Long before the first telescope peered into the distant nebulae, humanity gazed at the stars and wove intricate narratives of creation and destiny. These are the religious and mythological cosmologies, rich tapestries of belief born from the collective imagination and spiritual longing of our ancestors. They are not scientific explanations, but profound cultural artifacts, offering frameworks for meaning, morality, and our place within a grander design. Think of the myriad creation myths found across nearly all cultures and religions. These aren't accidental stories. They are fundamental attempts to answer the most primal questions. How did everything begin? Where do we come from? What is the purpose of it all? From the ex nihilo creations, where a divine thought or word brings forth existence from nothingness, to the earth diver myths, where a creature plunges into primordial waters to bring up the very soil of our world. Each tale offers a unique glimpse into the human psyche grappling with the void. We see emergence myths depicting progenitors passing through successive worlds, evolving until they reach our current reality. There are also stories of creation through the dismemberment of a primordial being or the splitting of a cosmic egg, bringing order from an initial chaotic unity. These narratives, while not offering predictive models or verifiable data, resonate deeply within us, providing comfort, identity, and a sense of belonging within a vast and often terrifying universe. They speak to the why rather than just the how. And then there is philosophy, the steadfast companion to both science and myth in this grand inquiry. Metaphysical cosmology, as a branch of philosophy, has always sought to place humans within the universe in relation to all other entities. It ponders questions that, by their very nature, extend beyond the current reach of scientific experimentation and observation. Marcus Aurelius, the Roman emperor and Stoic philosopher, profoundly captured this essence when he observed, "He who does not know what the world is does not know where he is, and he who does not know for what purpose the world exists does not know who he is, nor what the world is." This isn't just a philosophical musing. It's an invitation to understand ourselves by understanding the greater whole. Consider the kinds of profound questions that philosophy courageously tackles, questions that perhaps science can illuminate parts of, but may never fully resolve. What is the ultimate origin of the universe? Does it have a first cause, or is its existence truly necessary? These lead us down pathways of monism, pantheism, emanationism, and creationism, all attempts to conceptualize the fundamental nature of being. We're the ultimate material components of the universe. Is it all just mechanism and atomism, or are there deeper principles of dynamism and hylomorphism at play? These inquiries push the boundaries of our understanding of matter and form. Perhaps most deeply, philosophy asks, what is the ultimate reason for the universe's existence? Does the cosmos, in its staggering immensity, have a purpose? This is the realm of teleology, the study of ends and purposes, a concept that sits at the very heart of human meaning-making. And in an age of ever-advancing scientific discovery, philosophy compels us to ask, does the existence of consciousness have a role in the existence of reality itself? How we know what we know about the totality of the cosmos? Does cosmological reasoning, whether scientific or speculative, truly reveal deeper metaphysical truths about the fundamental fabric of existence? These philosophical inquiries are not distractions from scientific progress. Rather, they're the rich soil from which our scientific curiosity has often sprung. Indeed, the very origins of ancient Greek cosmology, attributed by some historians to figures like Anaximander, were deeply philosophical, seeking rational principles to explain the cosmos, long before empirical science as we know it existed. The early Greek philosophers, through sheer intellectual force, attempted to understand the fundamental stuff of the universe, the arche, and the processes that govern its changes. As we look back at the historical arc of cosmological thought, we see a fascinating interplay. From the geocentric models of Aristotle and Ptolemy, which dominated for centuries and were deeply intertwined with philosophical and theological views of humanity's central place, to the heliocentric revolution of Copernicus, Kepler, and Galileo, we witnessed an epistemological rupture. This wasn't merely a change in astronomical models. It was a profound shift in our understanding of our place in the cosmos, a philosophical revolution as much as a scientific one. Newton's universal law of gravitation, establishing that the same physical laws govern both terrestrial and celestial bodies, was hailed as a crucial philosophical advance, unifying the heavens and earth under a single, elegant framework. Even in the modern era of physical cosmology, the philosophical underpinnings remain. Einstein's general relativity, which truly kick-started modern scientific cosmology in 1917, challenged the very notion of a static, unchanging universe, opening the door to the dynamic, expanding cosmos we now observe. The great debate of the 1920s, concerning whether the spiral nebulae were distant island universes or part of our own Milky Way, was a contest of ideas that profoundly reshaped our cosmic perspective, settled by the observational genius of Edwin Hubble. The Big Bang model, initially proposed by a Belgian priest, Georges Lemaitre, in 1927, and later corroborated by Hubble's redshift observations and the cosmic microwave background radiation, stands as a testament to the power of both theoretical insight and empirical evidence. Yet, even as we revel in this golden age of cosmology, with incredible agreement between theory and observation, from the COBE, WMAP, and Planck satellites, to vast galaxy redshift surveys, there remain profound questions at the edge of our scientific understanding. Dark matter and dark energy, which constitute the vast majority of the universe's mass energy content, are still mysterious entities, hinting at physics beyond our current grasp. The precise nature of cosmic inflation, the earliest moments of the universe, continues to be an active area of research. So, while science provides the most reliable framework for understanding the physical universe, its age, its composition, its evolution, it cannot, and perhaps should not, be expected to answer every single question that arises from our contemplation of the cosmos. The human yearning for meaning, for purpose, for a narrative that places us within the grand scheme of things, continues to find expression in myth and philosophy. These disciplines, far from being obsolete, offer complementary pathways to wisdom, allowing us to engage with the universe not just as a collection of particles and forces, but as a source of awe, wonder, and profound existential inquiry. The universe, in its boundless expanse, invites not just our telescopes and particle accelerators, but also our poets, our philosophers, and our dreamers. It reminds us that while the facts of science are astonishing, the search for deeper meaning is an equally vital part of the human journey through the cosmos. As we drift into the quiet contemplation of these ultimate questions, we connect with a lineage of inquiry that stretches back to the very first humans who looked up at the night sky and asked why. And so, our journey through the vast, intricate tapestry of cosmology comes to a close for tonight. We've traversed millennia of thought, from the earliest philosophical stirrings to the latest cosmic revelations, glimpsing how humanity has wrestled with the profound questions of origin, structure, and ultimate destiny. I hope this deep dive into the universe's story has offered you moments of reflection, focus, or even peaceful slumber. If you connected with this cosmic narrative, please consider liking this video, sharing your reflections in the comments, and sharing it with friends. And of course, if you wish to continue these explorations, do subscribe and hit that notification bell. I'm always eager to hear your thoughts. What cosmic mysteries or scientific wonders would you like us to explore next? Until our next journey across the cosmos, keep looking up